Breadth first search. Breadth first search is an algorithm that traverses a graph level by level. Now before we go into actually writing the code, let us recap the steps we took in the breadth first search algorithm. We take our input as a graph, and as the aim we want to traverse that graph. What do I mean by traversal? I want to visit all the vertices and edges. So initially all vertices are unvisited, all edges are undiscovered. Then we choose an arbitrary start vertex. We add it to the first level and we visit it. Now, for all edges incident on that vertex, we are going to check if it's undiscovered. If it is an undiscovered edge, we check the vertex that follows the undiscovered edge. If that vertex is visited, we mark the edge as a cross edge. If that vertex is not visited, then we mark the edge as a discovered edge. We visit that vertex and we add that vertex to the next level. Now, once none of the edges incident on the vertex are undiscovered, we start exploring the next vertex. So with this in mind, let's start writing the code. So my algorithm is going to be called BFS, and as input it will take in a graph G. Now first we say that all vertices are unvisited and all edges are undiscovered. So now we have satisfied the initial conditions. Now we have to choose an arbitrary start vertex. So I'm going to say, for a vertex S that belongs to G dot vertices, I need to perform some steps. The first thing I do is I need to add it to the first level. So how are we going to implement these levels in our code? We are going to use a list. Whenever I want to add a vertex to a level, I will add it to a list. So I'm going to add to the end of the list the vertex S. After that, I am going to visit S. Now, for all vertices in level 0, I'm going to take the vertices one by one and do these steps. So I need to remove the vertices one by one. So I'm going to say, while the list is not empty, I'm going to retrieve the first vertex from that list. In level 0, there is only one vertex, so I'm going to retrieve that. Now, what must I do to this vertex V? I need to check all the edges incident on that vertex. So, for all edges incident on V, what must I do? I need to check whether it's undiscovered. After I check if it's undiscovered, I need to check a few things about the vertex that undiscovered edge leads to. Let's say that adjacent vertex is going to be W. So the adjacent vertex to the vertex V, which we arrive at through the edge E, is going to be W. Now if W is a visited node, then we mark that edge as a cross edge. If W is an unvisited node, then we set the edge to a discovered edge. We visit that node and then we add it to the next level. So now the question arises, how are we going to add to the next level? What I am going to do is, I am going to add W to the end of the list. So you may ask, how is this going to achieve adding W to the next level? Now, our list is a set of vertices and it contains all the vertices of level 0 followed by all the vertices of level 1 followed by all the vertices of level 2 and so on. Now every time I explore a vertex, I am removing a vertex from the front. So in what order am I exploring this set of vertices? I am exploring everything from level 0, then everything from level 1 and so on. Whenever I want to add a node to the level or to the next level, I add it to the end of the list. In this way, we can implement the levels in our code. Now, we do this for all the edges. And we do this until the list is not empty. And with that, we come to the end of our function. So we can see how this code works using an example. Let's say that this is our example. In the beginning, all the vertices are unvisited and all the edges are undiscovered. We are going to select a start vertex arbitrarily. So let's say I'm going to select A. I'm going to add A to the end of the list. Now I'm going to visit A. Now, while list is not empty, yes, the list is not empty, I'm going to remove the first element from the list and store it in V. So I'm going to remove A and now my V is going to be A. So for all edges incident on A, so these three, so let's start with this one. If it's an undiscovered edge, yes, it's an undiscovered edge. W becomes the vertex that follows. So W is B. If W is visited, no, B is not visited. If W is unvisited, yes, B is unvisited. So then what must we do? We set the edge to be a discovered edge. We visit that W and we add W to the end of the list. Now we go to the next edge, incident on A. We go to this edge. C is not visited and this is an undiscovered edge. So this is going to become a discovery edge. I am going to visit C and add C to the end of the list. I go to the next edge, incident on A. This is an undiscovered edge and this is an unvisited vertex. So I'm going to make it a discovery edge. and visit it. I'm going to add D to the end of the list. Now I go back here. Are there any more edges that are incident on A? No, there are no more edges incident on A. So we go to the next iteration of this loop. While list is not empty. Is the list empty? No. So we can go to the loop. V is equal to list dot remove front. So I'm going to remove B from the front of the list, and that is going to be my V. So now for all edges incident on B, so let me take this edge. If it is an undiscovered edge, yes, this is an undiscovered edge. Now suppose the adjacent vertex is visited, what must I do? I need to set the label of E to a cross edge. Let's say I represent a cross edge like this. Now I go to the next edge. Yes, there is an incident edge on B and it is undiscovered. It leads to an adjacent vertex which is unvisited. So what must I do? I set the edge to discovered. I visit this vertex and I add this vertex to the end of the list. Now I go back to this loop. Are there any more edges that are incident on B? No. So the loop ends and I come to the next iteration of the while loop. While list is not empty. Is the list empty? No. V is equal to list dot remove first. So I remove C from the list and C is going to be my V. Now for all edges incident on C, let's take this one or even this one. So I take this edge, I go to a vertex E. E has already been visited, so this becomes a cross edge. I go to this vertex or this edge. This edge is undiscovered. It leads to an unvisited vertex. So I make a discovery edge and I visit this F and I put F to the end of my list. Then I go to this edge. This is an undiscovered edge. Leads to a visited vertex, so it becomes a cross edge. Now I see, are there any more edges incident on C? No. So my for loop ends. So I go to my next while loop iteration. V is equal to list dot remove front. So I remove D from the front of the list. I'm going to now go for all the edges incident on D. I see that there is an edge here. If it is undiscovered and it leads to a visited vertex, I make it a cross edge. Then I go again. Are there any more edges incident on V or D in this case? No. So my for loop ends. I go to the next iteration. I remove the first element of the list, E. Then I see, for all E incident on V, are there any E's that are undiscovered? No. So my for loop iterates and ends. So I go to the next iteration of my while loop. I go to F. Are there any undiscovered edges from F? No. So my for loop ends without any substantial statements being executed. And I remove it. And I go to the next iteration of my while loop. Now while list is not empty. However, in this case, the list has become empty. So now my while loop ends. And with that, as you can see, we have visited all the vertexes and no edge is undiscovered. So this is how this BFS pseudocode works. Now, it is important to note that this code will only work if the graph is connected. This code does not work for a disconnected graph. Let me give an example. Let's say this is a disconnected graph we want to work with. And I'm going to start with my arbitrary start vertex as A. So I'm going to visit A. Then I will look for all the edges that is incident on A. I will find this one. I will visit B and this will become a discovery edge. B will not have any incident vertexes and so the algorithm will end. But in that case, only A and B would have been traversed. C and D are not traversed. So what can we say about this? This algorithm will only visit those vertices and edges that are connected to our arbitrary start vertex. So how do we modify this algorithm such that it can be used for disconnected graphs as well? What we must do is, for all S belonging to G dot vertices, if S dot label is equal to unvisited, we must perform this. So now let's see what the algorithm looks like. Let's say my arbitrary start vertex is A. I'm going to add A to the end of the list. I'm going to visit A. Now, while the list is not empty, I'm going to remove the first element. Then I'm going to look at the edges coming from that element. I have an undiscovered edge with an unvisited vertex. So I'm going to make that a discovery edge and visit this. When I visit it, I'm going to add it to the end of my list. Now I go to the next iteration of the while loop. List is not empty. So I'll remove B from the beginning of the list and I will look for undiscovered edges. There are no undiscovered edges incident on B. So I will exit the for loop after this. Now I will check while list dot not empty. But over here the list has become empty. Now the while loop will end and I will come back to this for loop for all S in G dot vertices. So I have taken A. Now let me take B. If S label is unvisited, B is visited. So we will not perform any of this. Now I'll go to my next vertex. I have C. C is unvisited. So I will perform these steps. I will first add C to the end of the list and I will visit C. Now, while the list is not empty, I'm going to remove C from the list and set it to V. Now for all edges incident on V, I'm going to search for undiscovered edges. So I find an undiscovered edge leading to a unvisited node. So I'm going to set it to a discovery edge, visit that node and add that node to the end of the list. Now, while list is not empty, I will remove D from the beginning of the list. I'll set it to V. I'll search for an undiscovered edge. There are no undiscovered edges, so I will come out of the while loop. Now I have come out of the while loop, I will come back to this for loop. Now, for all S belonging to G dot vertices, I'll go to D. If D is unvisited, no, D is visited, so I will not perform these steps. I'll go to the next iteration of the for loop for all S belonging to G dot vertices. We have already covered A, B, C and D in this for loop. So there are no more vertices to explore. So I will come out of the loop. In this way, we can modify the BFS pseudocode which we have seen to accommodate disconnected graphs. So this is how you write the pseudocode for breadth first search.